Okay. 2 stationary patrol cars. Y'all are driving. This might come in handy if you know this. 2 patrol cars are equipped with radar. Oh, how far? And they're 5 miles apart.
I'm trying to stay away from the police.
Yeah, but you can't always do that. As the truck passes the first patrol car, its speed is 55 miles an hour. So they're okay. They're driving speed limit or under. 4 minutes later, it passes the second patrol car, and the speed's 50 miles per hour. We want to prove that he had to have exceeded 55 miles per hour at some point during the 4 minutes.
What?
He had to have, because there's a place where the instantaneous rate of change equals the average rate of change. We're thinking mean value theorem. Yes, he would have had to have gone more than 55 miles per hour in that interval. So let's think about how we can apply the mean value theorem.
It took 4 minutes, right? That's right.
All right. We said the average rate of change is f of b minus f of a over b minus a. That's the average rate. Some point in that interval, the instantaneous rate of change and the average rate of change are the same. How does speed, and these are velocities, how does speed relate to velocity? Absolute value. Okay. So he's going miles per hour, but we're talking 4 minutes. So how much of an hour is 4 minutes? 4 over 60, which is 1/15 of an hour. Okay, 1/15 of an hour. So, how far did he go? At 1/15 of an hour, he's gone how many miles? 5. Because they clocked him. We'll let where they started clocking him or where they caught him the first time be 0. And then he went 5 miles. So the change in distance was 5. And the change in time is 4 minutes or 1/15 of an hour, since we're trying to figure miles per hour.
That's 150. You wrote 150.
Okay, so change in distance over change in time gives me velocity. If I simplify this, we get 5 over 1/15, which is 75 miles per hour. So he did exceed the speed limit over that 4 minute at least once. Yes.
So why did you put the zeros in for?
Okay, this was where he started. Change in distance over change in time. Just so that you could see that, maybe use it differently. But this is a practical application of the mean value theorem. I'm sure all their radar and their computers have this already programmed in, but that's what they were able to use to get all that programmed in. So if you get stopped and then you know they clocked you at 2 different places, it's not going to do you any good to say, no, I didn't speed. Michael.
Okay, so it's
All right. Assignment is on page 172. 5, 11, 15, 19, 25, 29, 33. It just seems like more when I list them out.
He's more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9.
The extreme value theorem said that if we had a function that was continuous and differentiable on a closed interval, that there's at least one minimum and one maximum on that interval. And we saw that when we have a closed interval that those values could occur at endpoints. But today we want to look at Rolle's theorem, and that's R-O-L-L-E-S. again, it's a function that has to do with a continuous differentiable function. So if our function is continuous on a closed interval, and differentiable on an open interval, and I'm just going to abbreviate differentiable. The reason we say differentiable on the open interval is because it may not be differentiable at the endpoints. We saw that with our square root function that was the upper half of a circle. It's continuous, and it was differentiable everywhere except at the endpoint. So if f is a function that is continuous on a closed interval and differentiable on the open interval, if f of a equals f of b, in other words, the endpoints have the same value, then there's at least one number c or one x value, but we'll just say there's at least one c on the interval such that the derivative is 0. In other words, there's at least one point where the derivative is 0 if the endpoints are the same, have the same y value. Now we can think about that if we have a function maybe that looks like this. F of A is f of B. Is this function continuous? Is it differentiable? It is. It's differentiable. And we see that there's at least one value where we would get a horizontal tangent. So Rolle's theorem would apply to that kind of a function. Okay, here's A, here's B. What about here? Will Rolle's theorem apply? Why not, Emily? It's not differentiable on the interval. Okay? There's a minimum value, but Rolle's theorem says there's at least one place where the function is, the derivative is equal to 0. But Rolle's theorem will not apply to this particular problem because it's not differentiable on the interval. So let's look at an example of how you might use Rolle's theorem. And I have seen, there are other ways to answer these kinds of questions, but I've seen some multiple choice questions on the AP where Rolle's theorem, if you remember it, is very handy and you can real quickly find the answers. So it is a theorem that can be useful to us. All right, let's say that we have this function. And I want to find the x-intercepts and show that somewhere in between those x-intercepts I have a derivative of 0. So first of all, we've got to determine, does Rolle's theorem apply to this function? Is it continuous? How do you know it's continuous? It's a parabola. It is a polynomial function, and every polynomial function is continuous, and every polynomial function is also differentiable. So the fact that we see it is a parabola, but the fact that we see it's a polynomial function, which means no variables in the denominator, no fractional exponents, it's a polynomial function, so it's continuous and it's differentiable. So if we find the x-intercepts, that means that those two x values would have the same y value, right? How do I find those x-intercepts?
You do the derivative
Set this equal to 0 and do what? And how do we do that? We factor. So what are my x-intercepts? X equals 3 and x equals -2. That means that f of -2 equals 0 and f of 3 also equals 0, because that's what we just found. Now we can look at this and see if we can determine where we have a horizontal tangent. How would I go about doing that? Find the derivative. And the derivative is 2x minus 1. So what x value gives me a derivative of 0?
Or 1/2.
X equals 1/2. All right, so we just found the value where we would have a derivative of 0, which means if we plugged it in, it would give us a maximum or a minimum value, right? That's the same as a critical number. All right, another example where we get more than one. All right, does Rolle's theorem apply? I want to find all values of C in the interval 2, 2, such that f prime at C equals 0. First of all, will Rolle's theorem apply?
Yes.
How? How do we know that? Grace?
It's continuous
It's continuous and
and it's differentiable.
differentiable. All right. So I want to find when f prime of C equals 0. All right. So let's make sure that Rolle's is still going to apply. We also have to check those that I put 2 and 2, but I meant -2 and 2. So let's check f of -2, because if we don't get the same value, then Rolle's theorem doesn't apply. What is f of -2? 2 to the 4th is
8. Well, sorry.
16 minus,
8.
what's f of 2?
The same.
Okay, so now Rolle's will apply.
So do those have to be the same for it to?
They have to be the same for Rolle's theorem to apply.
So you just talk about every part.
Yes, if you want to use Rolle's theorem.
So, just make sure.
That's what we've been talking about. I'm sorry, Megan, what was your question? All right. So let's find the derivative. Paul, what's the derivative?
It looks like 4x cubed minus 4x.
Okay, so I want to find where does this derivative equal to 0? Because I want to know where in this interval does f prime of C equal 0.
Okay.
So
set that equal to 0.
Mhm.
And, oh, I think you can take out an x.
take out an x. Anything else I can take
Oh,
out?
and a 4.
And what am I left with?
Let's see, x squared minus 1.
Okay, so what values would give me a derivative of 0?
X squared equals the square root of 1, which
What-
is just 1.
X equals 1, x equals
0.
0, and x equals -1.
Right.
Okay. So those are the three values in the interval for which the derivative equals 0. So you don't have to have just one. You can have more than one. Yes, ma'am.
Why is it 0?
Oh,
This is a factor.
Oh, okay, yeah. I got it.
How come on the example before you didn't take the derivative, but you did on this one?
We
To
did
get-
take the derivative.
But like to get the first x's. To get these two x's, you used the regular and then,
Okay, because I had to find the x-intercepts. I wasn't given an interval,
Oh, so that's what
so
you
I found the x-intercepts.
She's on the arch.
All right, now let's look at the mean value theorem. And the mean value theorem a mean has to do with an average, remember. You can use MVT to stand for the mean value theorem. Okay, again, a function has to be continuous on our closed interval and differentiable on the open interval, because we don't have to be differentiable at endpoints. Then there exists some number there exists a c, some number c, in the interval such that the instantaneous rate of change is equal to the average rate of change. Remember when we looked at average value versus the instantaneous, the average rate of change versus the instantaneous rate of change. This looks like our familiar friend. What was the formula that we first called it?
Oh, the limit.
Well, it was part of the limit, but even before that.
Changing.
This was our old friend, the slope formula, which was a rate of change between 2 points. But you're right, in calculus we started looking at it as a limit. But there's some point on the interval where the instantaneous rate of change equals the average rate of change. If we think about it graphically, let's say that our function looks something like this. There's some point where the slope of the secant line and the slope of the tangent line are the same. So here would be our C value. There's some point where the slope of the secant line between the endpoints is the same as the slope of the secant line or the tangent line. Rolle's theorem really was the same thing, because what's the slope of the secant line if they have the same value? 0. And we were saying that there is some point in the middle whose slope is 0. So that's just a specific application of the mean value theorem. But we'll use the mean value theorem and refer to it a lot this year. First of all, for it to apply, the function has to be continuous and differentiable. If it's not, mean value theorem does not apply.
It has to be a CD.
Yes, a CD. All right. And simply what it's saying, instantaneous rate of change equals average rate of change. All right, so let's do a couple problems. Any questions before we go on? Because you're familiar with this, you're familiar with both of these formulas. You know how to take a derivative now, and you know how to find an average rate of change. So let's look at a function. Keep that. F of x equals x plus 1 over x. And I want to find all the values in the interval from 1/2 to 2 such that f prime of c equals f of b minus f of a over b minus a. In other words, equals, yes. Thank you. Okay, I want to find all the values in that interval such that the instantaneous rate of change equals the average rate of change.
Is that f of b minus?
F of b minus f of a over b minus a. All right, so we need to figure out what is f of b and what is f of a. So what is f of a? When x is 1/2. That's going to be what? 1/2 plus 1, 3/2 over 1/2, which is 3. What is f of b? 3/2. All right. So f of b minus f of a is going to be f of 2 minus f of 1/2 over 2 minus 1/2. We've already figured out what f of a and f of b are, so I can fill them in. 3/2 minus 3 over 3/2, which is 3/2 minus 6/2 is negative 3/2 over 3/2 equals negative 1. So the average rate of change is negative 1. 3/2 minus 3. 3/2.
So negative 1 is what?
That's the average rate of change. I want to find where the instantaneous rate of change is the same.
You said that again.
We've got to find the derivative of the function. Okay, so yes, you're right, Anna. We've got to find the derivative and set it equal to negative 1. So let's make this easy. Can I simplify that derivative?
Times x.
How can I simplify it? The derivative. Everybody stand up for just a minute while we do this. Stand up so you can wake up. Is this the same function as my original f of x?
Yeah. Well,
Yeah.
Which one's easier to take the derivative of?
I
The
said
first one or this second one?
I said the top one.
You think the top one?
Just quotient rule.
Yes.
Well, do we not have to use a quotient rule in the bottom one?
you don't.
Well, this is the same as 1 plus x to the negative 1. What's the derivative of 1?
Also, negative
I guess you
1
could
over negative
x over 1 over x squared, right?
Yes. Yes. You can use a quotient rule. I don't care if you use a quotient rule. If that helped you wake up a little bit, you can sit back down. Grace, your eyes look heavy. When you eat a big meal, then it's hard to stay awake. It wasn't very good. Then, okay. So you can use the quotient rule, but you'll get the same thing. So now what do? We need to know where does the instantaneous rate of change, which is this, equal the average rate of change. So I'm going to set them equal to each other. So we want to know where does negative 1 over x squared equal negative 1. Multiply both sides by negative x squared. We set our average rate of change equal to the instantaneous rate of change, or the derivative. So x equals plus or minus 1, but which one of those is in our interval? X equals 1 is in the interval.
Why? What about x equals negative 1?
Because when we solve this, we get plus or minus 1.
So what about negative 1?
It's not in the interval. It's not in the interval. right, practical application.
Well, rainy goodies, these are the best.
Yes, they're the best.